after running your regression model to get the sample regression line, you might wonder, does it fit the data, or how well does my model fit the data? So for example, you have this scatter plot of data, right? And you fit the regression model, the y hat, and you wonder, okay, what do I have to or how can I know if this is a good fit or not? Well, you have two measures, and that would be the R-squared and the standard error of the regression. So if we look at the R-squared, it's the fraction of the sample variance of y, which is explained by x in your model. For example, if the R-squared is 0.25, then we say that we often say this in percentages. So we say that 25% of the variation in y is explained by x. So how do you calculate the R-squared? It's actually the explained sum of squares divided by the total sum of squares. And how do you calculate those? Well, you have the total sum of squares would be like this. The regression line there, you have x, you have y, and here you have some data points. But if you draw a line straight in the middle here, this would be y bar. This would be the sample average of the y variable. Then R-squared is basically a number which gives you how much of the variation, the total variation, is explained by including x in the model. So the total sum of squares looks at the data point minus the average of the y and squares it. So it looks at this, at these differences, or okay. So the total sum of squares just looks at the difference between the observation and the average, okay? And the explained sum of squares is a bit different, okay? It's the y bar here, the average of y, but it looks at the fitted line for that x value minus the average, okay? So it looks at the fitted line. So let's try to keep them as similar as possible, because you have the data points, right? And here, and you go from the fitted line down to the average line, okay? Oh, sorry, that was wrong. So you have these differences. So in most cases, if x is actually beneficial in explaining some of the variation in y, then these these kind of residuals from the fitted line to the average, they would be lower, or yeah, they would be lower than in absolute value than if you look at the data point, the difference between the data point and the average line. Okay. So if you want to calculate the R squared, you just add up all these squared differences for the explained sum of squares, and you add up the squared differences for the total sum of squares, and you take the explained sum of squares divided by the total sum of squares. Okay. And immediately you know that, or you notice that if the regression line was horizontal, okay, that would mean that no matter which value of x you look at, the slope would be 0, and no matter what kind of x value you look at, the estimated y would just be the average of y. Okay, so and in that case the R squared would be 0, because these residuals between the y hat and the average of y would be 0. So actually, the R squared is quite useful if you only have one x variable, because the R squared is then the square of the sample correlation between x and y. So if you take the square root of the R squared, for example, you take the square root of the R squared, would be the sample correlation between x and y. Okay, and because of this mathematical setup, the R squared ranges from 0 and 1%, and if you have an R squared of close to 1, that would indicate that x would be very good at predicting the variation in y. It would mean that the data points, they are quite close to the fitted line. Okay, well, an R squared close to 0 indicates that x does not contain much information in explaining the variation in y. So, and one important point is that R squared is unit free. So it's not measured in anything. So it's not measured in kilos or liters or euros or whatever. So that was the R squared. We also have the standard error of the regression, and this is denoted as u hat. The standard error of the residuals. This is just the estimator of the standard deviation of the difference between the actual values and the fitted line. So this is, well, you remember from our previous video that you have the fitted line, the y hat, and you have the actual observations, and then you would have the residuals here, which is the difference between the data point and the fitted line. So it's the data point minus the value of the fitted line. Okay. So here you have positive residual and you have a negative residual, and you have a positive residual, no, negative residual again, and a positive residual. Okay. And here the formula for the standard error of the regression is given by this, and you see that this is just the sum of squared residuals, right? In the numerator. So then you just calculate the sum of squared residuals. You divide by n minus 2. N is the number of observations, and the minus 2 is due to that you calculate these residuals by estimating two parameters, which is the intercept and the slope, the beta naught hat and the beta 1 hat. So you kind of spend 2 degrees of freedom calculating these residuals. So and something which is important is that the units of these standard error of the residuals are the same as those of the y variable. So if the y variable is measured in euros, then the standard error of the residuals is also measured in euros, and we use the R-squared and the standard error of the regression in 2 different ways, which we will take a look at. But a high R-squared means that the standard error of the regression is low because the data points, they are fitting quite snugly onto the fitted line, and a low R-squared means that the residuals, they are not very close to the fitted line. So, and a high R-squared does not mean that the regression indicates a causal relationship between x and y. It doesn't. It just means that x is very good at explaining the variation in y, and that if you just flip the regression, so you just rename the x variable y and the y variable x, then you get actually the same R-squared as if you do the other way. So there's no causality in this setup, which a lot of people actually miss. Okay, so it's quite common that a high R-squared means that, well, I've found a causal relationship, but don't do that. You only find a causal relationship if in theory you can say that x causes y. So this is why you have to not only look at the data, you have to know what kind of data generating process you are dealing with. You have to know your business, okay? Otherwise, anyone could do econometrics just by pressing a button. So you can also find a causal relationship between x and y if you do this randomized trial, which we already touched upon in a previous video and we'll touch more upon later on. And quite important, you cannot compare R-squared between two regressions that you do not have the same response variable, the same y, and or do not use the same data set. So for example, you can't, for example, if you have the y equals beta naught plus beta 1 hat x, and in a different model you use the logarithm of y. You have changed the y variable, but you are estimating a linear relationship. You can't compare the R-squared between these two regressions, even though one is higher than the other, because the response variable, the y, is not the same. Likewise, if you have the same setup, the y equals beta naught hat plus beta 1 hat x, and use the same, estimate the same model on a different data set, you can't compare the models either. So that was it for evaluating the fit of our regression model. We will come back to this later on when we look more into regression analysis.